Welcome to the last session of our first morning talks. We have covered the CMB in some detail. This evening we are going to have a panel. And to close the session, I cannot think of a better speaker than André Koch Torres Assis, who we also found through the podcast, and who is one of those people who has thought so deeply about not just the modern questions of cosmology, but the art and practice of science, that every time that I listen to him talk and explain something, I feel like the entire world is opened to me in a way that I had not seen before. And so it is my great pleasure to introduce Dr. André Koch Torres Assis, who will speak to us about the apparent cause of the cosmic background radiation.
The scientific revolution starts now!
DemystifySci podcast.
Let us see in the dark!
What I will present today is a topic which I have been working for 30 years. My papers with a colleague of mine from Brazil, Marcos Neves. And those of you who wish, you can go on to my homepage, and the papers are there with all the references and so on. So I will talk more about history of science here, specifically about the history of the cosmic microwave background radiation. And I am very happy that Shiloh and Anastasia got interested in this topic and invited me to come here, because our publications for 30 years ago had not so large impact as we did expect originally. When we read the newspapers, magazines, divulgation of science, nowadays homepages, and research papers, they always say that the cosmic microwave background radiation is the strongest pillar of the Big Bang, especially because it was predicted before its discovery by Penzias and Wilson in 1965. And it was predicted by the Big Bang, and they just say sometimes the name, Gamow. But they only say that in general. They don't give the references, the data, or when were these predictions made. But this is everywhere. In textbooks on astronomy, cosmology, we learn that at the university. But is this true? Here are the facts, okay? The real predictions made by the Big Bang. The oldest one was not made by Gamow himself, but by two of his students, Alpher and Hermann. And they did publish a paper in 1948. That is the oldest prediction made by the Big Bang that I am aware of. And they said 5 Kelvin. Then next year, Alpher and Hermann did publish another paper, Physical Review, and they said bigger than 5. Then the first paper by Gamow, it was in 1953. I believe it was in a Swedish journal or so on. And in that paper, he said 7 Kelvin. Then he wrote a book, Gamow. The title is The Creation of the Universe, a very religious book. And in this book, I will quote from the second edition of this book, which is from 1961. There is only one page where he discusses or talks about the temperature of space. And in this page of the second edition, 1961, He said 50 Kelvin. You see, this is almost 20 times higher than the known value that we have today. By Alpher and Hermann, that is 100% mistake, because temperature is 2.7, 2.5, let's say. So they said 100% mistake, 5 Kelvin. But with Gamow, it is 50 Kelvin. And then in 1965, Penzias and Wilson did publish their paper, in which they arrived at the temperature 3.5 plus or minus 1 Kelvin, utilizing a horn antenna built to study radio astronomy. So these are not so good predictions, but there are predictions. Okay, but this is not the whole story. What the textbooks, the Wikipedia, and anywhere, the newspapers, the magazines, they don't tell is that there are another much better model of the universe, that the universe is infinite, has always existed, and is infinite in directions as well. And people working in this topic, they also made predictions and made on experiments. And this will be my main topic today. I will talk about predictions based on an infinite universe without expansion, without Big Bang. I will talk about Charles Edward Guillaume, 1896, 5.6 Kelvin, before the birth of Gamow and his students, because Gamow was born in 1904. Then Eddington in 1926, 3.2 Kelvin. Then in 33 and 38, Erich Wegener and Walter Nernst, the father of the third law of thermodynamics, 2.8 Kelvin, which is the value that we have today with COBE satellite. 1941, Mackellar and Hertzberg, there is a Z here, I forgot, 2.3 Kelvin. 1953, Finlay Freundlich, between 1.9 and 6 Kelvin. 1954, Max Born, Nobel Prize, when discussing the work of Finlay Freundlich, he said, if Finlay Freundlich is correct, the redshift is linked to radioastronomy, and the Broglie as well, starlight model. So I will discuss this. So the essence of my talk is in this picture. So if you keep in mind this picture, you can forget the 1,000 words that I will say today. But keep in mind this picture. The black lines are these exponential predictions based on the Big Bang. They begin with, this is temperature as a function of the year of the prediction. Alpher and Hermann, 5 Kelvin greater than 5. Then Gamow, 7 Kelvin, and then 50 Kelvin. And Penzias and Wilson found 3.5 Kelvin. All the red dots here are infinite universe, without expansion, without Big Bang. Guillaume, Wegener, Nernst, Eddington, Mackellar, Freundlich, and Max Born. All of them extremely close to the present value of 2.7 Kelvin. So this is the essence of my talk. Now I will just try to show how did these guys here, which you don't hear about them, how did they arrive at these values? Before that, all of these guys that I will talk today, they utilize the so-called Stefan-Boltzmann Law. This law is due to Stefan, 1875, empirically, and then his student, Boltzmann, made a theoretical derivation, 1884. The total energy radiated per unit surface area, per unit time, across all wavelengths for a black body is directly proportional to the force power of the temperature of the body. Okay? This is the Stefan-Boltzmann constant, but it's proportional to the force power. Another way of phrasing the Stefan-Boltzmann's law, the radiation energy density of the radiation field is also proportional to the force power of the temperature. Okay, this was just before Gamow that I will mention here. But all of the people you be discussing here, they utilize Stefan-Boltzmann's law. So implicitly, all of them, they are talking about a black body radiation temperature. Okay, all of them. So this is Charles Edward Gamow. He was a Swiss physicist, head of the International Bureau of Weights and Measure, president of the French Physical Society. In 1920, he got the Nobel Prize in Physics in recognition of the service he has rendered to precision measurement in physics by his discovery of anomalies in nickel steel alloys. Precision measurements. When he died, his obituary in the American Journal of Physics, they always quote his precision measurements. The president of the Bureau of Weights and Measures. So he published this paper in French, La température de l'espace, La nature, 1896. 5 years ago, I did publish with this colleague of mine a full English translation of this, just 3 pages. The translation was made by a colleague of mine from Canada, Roy Keyes. And we did publish that in the American Journal of Physics. So anyone can read in the original French and in the English translation. What did he do? He considered a black body which is in interstellar space, far from other stars. And then he assumed that an equilibrium state in which the radiation received by a black body, because if you have a body and it receives radiation, it will heat until one point in which it emits the same amount of energy that it absorbs. And so you can find the temperature of equilibrium in which what you absorb is equal to what you emit. So he utilized the Stefan-Boltzmann's law and the measured amount of radiation by the stars. Measured, not estimated. And then these are his words. We conclude that the radiation of the stars alone would maintain a test particle we suppose might have been placed at different points in the sky at a temperature of 5.6 Kelvin absolute. Okay? Equilibrium. You absorb, you heat a little until you emit the same amount that you absorb. And by Stefan-Boltzmann, if you know the measured amount of energy, you can estimate the temperature. That's what he did. Some years later, Arthur Eddington, English astronomer, physicist, and mathematician, he has a book called The Internal Constitution of the Stars, 1926. The last chapter of the book is called Diffuse Matter in Space. And there is a section called The Temperature of Space. He doesn't quote Gamow, but I guess he was inspired by Gamow. He had just won the Nobel Prize 6 years before, the same name, temperature of space. And he does the same calculation with better data. These are his words. The total radiation received from the stars has an energy density of 7 × 10⁻13 ergs per cubic centimeter. By Stefan-Boltzmann's formula, the effective temperature corresponding to this density is 3.18 Kelvin, 3.2, just like Penzias and Wilson. In a region of space, not in the neighborhood of any star, this constitutes the whole radiation field of radiation. And a black body, for instance, a black bulb thermometer, will there take up a temperature of 3.2 Kelvin so that its emission may balance the radiation falling on it and being absorbed by the thermometer. This is sometimes called the temperature of interstellar space. So this was known at that time. It's not an original calculation by Eddington. It is sometimes called by the community at that time. But until now, these two examples, I'm talking about the temperature inside our galaxy, interstellar space. But Hubble, in 1924, 5 years before the Hubble's law, okay, he found Cepheid variable stars in nebulae, including the Andromeda Nebula. His observations proved conclusively that some of the nebulae, not all of them, they are much too distant to be part of our galaxy. And so, since 1924, we know that there are external galaxies, okay? What I will talk about from now on is not inside our galaxy, but in intergalactic space. So I will talk about this German physicist, Erich Wegener. He was known primarily for the design and construction of instruments to measure cosmic ray intensity at various altitudes. There is I work in University of Campinas in Brazil, in an Institute of Physics, and we have 4 departments. Where I work is in the Department of Cosmic Ray. That's my own department at the University of Campinas. This is the subject, cosmic ray. And this Bruno Rossi is a textbook writer and so on. And he said the following about this Wegener. In the late 20s and the early 30s, the technique of self-recording electroscopes carried by balloons in the highest layers of the atmosphere or sunk to great depths underwater was brought to an unprecedented degree of perfection by the German physicist Erich Wegener and his group. To these scientists, we owe some of the most accurate measurements ever made of cosmic ray ionization as a function of altitude and depth. Wegener, he was the first vice president of the Max Planck Society in Germany. He was the founder of the Max Planck Institute of Solar System Research. Very important guy in Germany. What did he do? Now he made the same kind of calculation of Gamow and Eddington. But instead of utilizing the light of the stars, he did utilize the measured amount of energy from cosmic rays. And cosmic rays, some of them come from the sun, from the nearby stars, Sirius, and so on, but most of them, they come from outside our galaxy. How do we know that? For instance, the amount of radiation in the plane of the galaxy is essentially the same as orthogonal to the galaxy. So very little absorption by our own galaxy. So it comes from outside, most of it, some from the sun and so on, but most of it comes from the outside of the galaxy. And then he said the same. So let's assume that all of this is absorbed by a black body until it heats and emits the same amount that it received. What was his conclusion? 1933. So he analyzing the measured energy of cosmic rays arriving on Earth. He arrived at temperature of intergalactic space, not interstellar space. A celestial body which has sufficient dimensions to absorb cosmic radiation is heated by means of this cosmic radiation. The heating results to be proportional to the energy from the cosmic radiation in the surface of the body. It is heated until it emits the same amount of radiation, so that the black radiation becomes to the force power of the temperature and the surface of the body. The final temperature is determined by Stefan-Boltzmann's law and is found to be 2.8 Kelvin, the same that we have nowadays with CMB satellite. This cannot be a coincidence. This cannot be a coincidence. It is a precise, he was a guy from precise measurements. Now, his work by Wegener, it was discussed by Walter Nernst, German physical chemist, father of the third law of the thermodynamics, 1906. And he received the Nobel Prize in the same year as Gamow. Gamow received the Nobel Prize in physics. Nernst received the Nobel Prize in chemistry, the same year, 1920, in recognition of his work in thermochemistry. He has some papers in German and translated into English, 1937 and 38, defending an infinite universe, boundless, homogeneous in large scale, without expansion. And he assumed that the cosmological redshift was due to a tidal-light effect, not due to a Doppler effect. He quoted Wegener's paper on temperature of 2.8 or 3 Kelvin. So you can read his works. I won't go into the details here, but all these references, they are in my papers. You can find them in my homepage, okay? And most of them, they have been translated now into English. 1941, Andrew McKellar, Canadian astronomer, he made the first identification of molecular matter in interstellar medium, identifying the spectrum of organic cyanuradical. In 1941, his analysis of the spectra of these molecules showed that the surrounding space was very cold, with a temperature of 2.3 Kelvin. Hertzberg, German-Canadian physicist, Nobel Prize in 1971 for his contributions to the knowledge of electronic structure and geometry of molecules. He quoted this estimation by McKellar, 2.3 Kelvin. But both of them, they did not recognize the importance of this value. Nowadays we know, but at that time both of them, that has little significance. But now we know that another way of reaching this temperature. Now I'm talking about equilibrium, okay? The energy you receive is equal to the energy you emit. Now I will talk about another prediction based not on this phenomena of equilibrium, but based on measurement of the redshift. Another kind of phenomena, but it should interest some of you in the room or someone who may be watching me in the internet later on. Each chemical element has a series of characteristic emission and absorption lines. For instance, hydrogen and helium, they have different lines in the visible spectrum. These are the main ones, okay? Qualitatively here. So when we look at one star, That is due to Kirchhoff and Bunsen. When we look at the sun, when we identify these lines, we know, okay, there is hydrogen there, or there is helium, or there is iron, or other atoms. So we can identify that by these lines. So this is spectroscopy. We don't need to go to the sun to know its constitution. And these lines, sometimes the same spectra, it goes to the red end of the spectrum. This is what we call redshift. For instance, the smaller the angular size of a galaxy, that's probably it is farther and farther away, the more the spectrum goes to the red end. So this is the redshift. So the smaller the angular size of a galaxy, the greater the redshift of the spectral lines. This is how we define the Z, the redshift, the wavelengths at the laboratory and the observed one. So it changed, but you know that it is, for instance, in this case, hydrogen. So now I will talk about a very interesting guy, Freundlich, German astronomer. I quote here some of his papers. 1954, after Hubble, okay? Hubble law, 1929. So Finlay Freundlich came after that. And I will quote some of his work and a paper by Max Born. Freundlich, he spent his whole life. He was an astrophysicist, experimental astrophysicist. He had two goals in life. I believe he was a fan of Einstein. He wanted to test Einstein's idea. So he spent 40, 50 years of his life trying to make two tests of general relativity. One of them was the deflection of light, okay? And the other was the gravitational redshift, that there is a redshift which depends on different potential energy. So these were the predictions by Einstein's general theory of relativity. And he wanted to test them. He built, I believe it was in Potsdam in Germany, an Einstein tower to make these measurements. He created an Einstein Institute and so on. And he spent 40, 50 years creating better and better spectroscopes and even building observatories. He needed to leave Germany because of the Nazis, and then he did go to Istanbul in Turkey, 3 years there, built an institute to develop, and then he received an invitation. He went to Prague, but he could stay only a short time because the Germans went into the Czech Republic, and then he received an invitation, and then he went to Scotland, okay? But all 40 years working with measurements of the spectra of the sun and stars, trying to test these two predictions. He organized 2 or 3 expeditions to measure the deflection, bending of light when it passed close to the sun, but due to bad weather, his measurements were not conclusive enough. But I will talk now about his testing of the gravitational redshift. So, we have some nebula, like Orion Nebula, which is inside our galaxy. There are some which are on other galaxies, but some of the nebula are inside our galaxy. We can measure their redshifts. But even inside the nebula, we can measure specific redshifts of some stars which belong to that nebula. And some of them, they are higher than the redshift of the nebula. These are anomalous redshifts. And so in 1953-54, he proposed a tired light model which could explain the redshift of many objects, A stars, the Sun, B stars, O stars, supergiant M stars, Wolf-Rayet stars, and white dwarfs. They have different temperature, which goes from 3,000 M stars, 6,000 kelvins for the Sun, up until 50 kelvins, and so on. And he proposed empirically a formula which is analogous to the Stefan-Boltzmann's law, proportional to the force power of the temperature and of the length that light moves through this radiation field. And in his paper, so he arrived at this formula here to explain the redshift of the stars. But in that paper he said, let us suppose maybe if this works so well for all of these stars, maybe the same mechanism is responsible for the cosmological redshift, which should not be due to Doppler. Let us suppose that it's due to the same formula, because we know that the redshift increases with distance. And by knowing the left-hand side by Hubble, he knew the value of that. We can estimate the temperature. We can reverse the argument. And then he said, we may have, therefore, to emphasize that the cosmological redshift is not due to an expanding universe, but to a loss of energy which light suffers in the immense lengths of space it has to traverse, coming from the most distant galaxies to the Earth. Thus, the light must be exposed to some kind of interaction with matter and radiation in intergalactic space. And you see, when he did apply this formula, he obtained for the stars. But when he did apply that formula to the cosmological redshift, he could estimate that if that formula is correct, we should have a black body temperature of intergalactic space between 1.9 and 6 Kelvin. Now, what I will show to you, please pay attention to the next slide, because now I will not talk about a faraway galaxy or a quasar that no one knows exactly what it is. I believe Houghton Arp is correct. But even we don't know what a quasar is. What I will talk now is the best star known to us, which is our Sun. What is the redshift of the Sun? Okay? So that was a work of this guy, Freundlich. This is a picture by this paper by Freundlich. So if we look at the Sun, this is the Sun, okay? So we have the center of the Sun and we go to the limb of the Sun. So when we go to the center, to the limb of the Sun, the redshift increases. We cannot see that with our naked eyes, but with spectrographs we can see that. So this plot shows that here is a function of the angle theta. I will just show what this theta is. But when this theta is 0, we are looking at the center of the Sun. And when we are here, we are looking at the limb of the Sun, okay, in any direction, okay? It is symmetrical. So the measurements and this straight line here, that is the prediction of general relativity. If the redshift of the Sun is due to a gravitational redshift, it should not depend on the angle, because the gravitational potential is the same all over the surface of the Sun. So it should not depend on the angle. And even the numerical value, for instance, here at the center of the Sun, the measured value of the redshift is 20% lower than the prediction of general relativity, 1/5, okay? This is the prediction. And these crosses and dots here they are measured values. You see, some of these experiments, 1928, he puts his own experiments, which comes from 30 years before. And when Freundlich did publish this paper, he was 70 years old, after spending 40 or 50 years making these measurements, and tried to, I believe he wanted to show that Einstein was right. But after 50 years with these precise measurements, he could not find that. But these are not only experimental results. This dotted line here is a fitting, theoretical fitting of that measurements. And this theoretical fitting, it's a very peculiar one because it is proportional to the second of an angle. It's very unusual result because normally it is proportional to the sine or to the cosine. This time it is a law which fits with the second of an angle. What is it? Let me show to you. Here we have the sun at the right. The Earth is somewhere on the left, okay? The sun is emitting light towards the Earth. And the sun has some atmosphere, which has a thickness h, okay? And if we look, the light which comes to the Earth, if we are looking at the center of the sun, it needs to cross a thickness h of the atmosphere. But if we are looking closer to the limb, it needs to cross a larger distance, d. By a simple triangle, the cosine of this angle theta is h over d. So d is h divided by the cosine, so which is h times the second of the angle. So what this empirical fitting shows is that the redshift is proportional to the length of path which light goes through the atmosphere of the sun. So to me, this shows clearly that the best known stars in our neighborhood, that it shows that the redshift is due to interaction of light with the medium in the atmosphere of the sun. And maybe even this constant here is a small portion which comes from the sun until the Earth. So this conclusion to me is so, I believe that Freundlich arrived at a huge step forward, but his working has been forgotten, neglected. But I tell you, go to see this guy. I believe he struck gold at the end of the rainbow, okay? I believe that formula is the correct one because it cannot be a coincidence. So many things he did find correctly. So, Max Born, he was a Nobel Prize in 1954 for his fundamental research in quantum mechanics, especially in the statistical interpretation of quantum mechanics, wave function. Max Born did publish a paper following Freundlich's paper, and the paper is called On the Interpretation of Freundlich Formula. And then Max Born discusses if Freundlich's ideas make sense or not. And these are his conclusions in this paper. Max Born on the Interpretation of Freundlich Redshift Formula. Proceedings of the Physical Society, 1954. He shows that Freundlich did believe that it was some kind of photon-photon interaction. And then Max Born said, if that is the case, we can calculate the wavelengths of the cross-section of this photon-photon interaction, and so on and so on. And then there is a sentence in this paper. So, thus, if Freundlich is correct, if the mechanism proposed by Freundlich is correct, redshift is linked to radioastronomy. That was Max Born, 1954. 11 years later, Penzias and Wilson measured this 3 Kelvin temperature with a horn antenna, which is shown here, built to study radioastronomy. This cannot be a coincidence. I believe Freundlich is right. Max Born is right. Maybe it might not be photon-photon. Maybe it is light and electron, or light and an ion, or proton. I don't know, but it must be interaction, and light and the intermediate medium. So for those of you who wish, we have this translation of Gamow in 2020, and we have some papers 30 years ago on these topics, okay? But you can find them in our homepage. So in conclusion, the cosmic microwave background radiation with a temperature of 2.75 Kelvin is a proof against the Big Bang. These are historical facts. You cannot change them. These are publications. Why? Because it was measured, the background energy of the stars, cosmic rays, and so on, and sun. And they were predicted earlier and much better than the Big Bang. So, thank you for your attention.